Hi, my name is Paritosh Mokhasi. I'm a kernel developer at Wolfram Research in the numerics group. Today I'll be talking about finite element methods as it is used in ND-solve. We'll be going over various examples, and we'll be talking about error analysis as it pertains to finite element methods. Thank you. So let's get started on this, on finite element methods. So for those who are new to ND-solve, ND-solve is one of those super functions in Mathematica that allows you to solve differential equations, large variety of differential equations. It could be boundary value, ordinary differential equations, DAEs, what have you. And I'm going to focus on these partial differential equations and how finite element methods are used to solve PDEs. Now, I want to point out, for those who are interested in finite element methods, is that there's a lot of documentation in Mathematica, but because the documentation is so vast, sometimes you might not be able to find the right page. So we have basically put together all the links to the relevant documentation. So once you have the notebook, just go ahead and click through them, and it'll take you through the various math associated with finite element methods, how to use it in ND-solve, different methods, what have you. So. Okay, so how do you use finite element methods in ND-solve? Well, just as you would solve any partial differential equation, you need three things. You need a governing equation, which is the first one here. You need the domain in which you're going to solve the problem. That's the second one. And you need a set of boundary conditions, which is the third one. And once you have formulated these three things, you just present that to ND-solve in the form that is similar to how you would give any differential equation. You give it the equations and the boundary conditions. You give it the dependent variable for which you want the solution, and you say that the independent variable belongs to this domain. And you go ahead and run that. Yeah, sure. And you get back an interpolating function, which is no different than what you would get from any other solution. It's got all the information embedded in it, and you can go ahead and use that interpolating function to plot, do any kind of analysis, and it just works seamlessly. So the finite element part of it is really not explicitly visible. It happens very seamlessly behind the scenes and just takes care of everything for you. So what kind of problems can finite element methods solve? Well, right now, maybe I should just make this a little bigger. Okay, right now it can solve only this one problem. Or a system of these problems. This is a very general linear system of equations. And depending upon what kind of coefficients, these D, C, alpha, gamma, beta, depending upon how they're set up or which ones are eliminated, you end up with different family of equations. You could have a Laplace, Poisson, you could have Helmholtz, wave equations, and what have you. So these are the kind of problems that we'll be talking about. Now, there is currently work underway that will allow nonlinearity to be handled by FEM. That's not in right now, but that's something we're working on, and it should be in very soon. Okay, so the second thing that I want to talk, or rather the main thing I want to talk about today are the boundary conditions and how you're supposed to apply boundary conditions to finite element methods in order to solve the problem correctly. Because without that, you're sort of you're just shooting in the dark if you don't understand how boundary conditions are implemented in finite element methods. So there are two types of boundary conditions that you can apply. One is the Dirichlet condition, and the second is the Neumann condition. Now, the Dirichlet condition applies to these red nodal points on the boundary, and the Neumann values are applied on the line segments that represent the boundary. Okay, so I'm going to now talk a lot about boundary conditions and the common gotchas and what you should be looking out for when you are dealing with specifying boundary conditions. I'll start with the Dirichlet condition. The Dirichlet condition is defined in this way. This is how you would present it to ND-solve. It's got two arguments. The first one tells you, what is the numerical value you want to put at the nodal location at the boundary at whatever location, and the predicate tells you which nodal values you should be applying that value to. So for example, in this case, which we are going to look at, which is the disk example, the boundary says that I want to put u equal to 0 for x greater than or equal to 0. So any boundary node that lies on the right of the plane is going to take on a value of u equal to 0. So how do you set it up? You set it up pretty much like I showed you before. You give the equation, the domain, and the boundary condition, and we specify that, and you solve and visualize. Really, that's pretty much it. You can see that on the right hand side, this is where the u equal to 0 has been applied, and then on the left hand side, which is it's basically left free, it picks up this whatever value it picks up from solving the system. Okay, so let's make things a little bit complicated, and we'll progressively make it more complicated. Let's start talking about multiple materials. So these are cases wherein you have two separate materials with different material properties that are connected to each other, and they share a common interface with each other. In that case, if you want to solve a Poisson equation, what happens then? So because there are two separate materials, they have different material properties. So the one material, which is setup is basically a disk, a solid disk within a disk, and they have different thermal conductivity. Okay, one has got 1, and another one is 10 times more, but they are given the same boundary condition, x greater than or equal to 0. So the way you set that up is by putting in this conditional statement saying that if it is less than or equal to 1/4, then use this diffusion matrix, and if it is greater, then use this one. Okay, and then you just set up the problem in this fashion, and when we run it, you see that this is the result you get. So it's slightly different from the first case, but if you rotate it, you see that at x equal to 1/4. At that inner disk, you end up getting this jump. So what is FEM doing? What is it doing internally? So if you look at the solution, let's see, Wolfram element mesh. Let's look at the wireframe, if I can type. Okay, when you see this element mesh, you see that there's an internal boundary has been applied. Okay, and that internal boundary represents that interface between those two materials. And so it picks up that internal boundary from the governing equations, puts that in there so that the interface is properly resolved. Okay, so that kind of parsing happens inside of NDSolve. And specifically within the FEM framework. So now that I've brought up the topic of internal boundaries, let me take you through one specific example wherein the user now gives a specification on the internal boundary itself. So it's going to be a Poisson problem on a disk, but now the boundary condition changes. The Dirichlet condition says that it's going to be 0 at the outer wall, and also at x squared plus y squared equal to 1/4. And I'm going to set it up in a very specific way. I'm going to use 2-element mesh here, and I set it up as an implicit region, and I provide the Dirichlet condition. Okay, really nothing more complicated than that, and you get a result. And you can see that now, because of the internal boundary that is specified, it forces it back to 0, and then goes back and gets started. Okay. Notice a couple of things. If you pay close attention, there are two things going on here. X greater than or equal to 0, you apply this. For the outer case, it takes on u equal to 0. So the external disk gets that x equal to 0 value only on 1/2 of its boundary. But the x squared plus y squared equal to 1/4, that gets applied everywhere. Okay. So that's one thing you need to take into account. But if it is very easy to become trapped in some of the subtleties here, especially when you set up your own domain. It's got all these bells and whistles with its internal boundaries, and then you go to solve a particular problem. You might expect some behavior that you weren't expecting. So for example, what would you expect to happen if I were to change the problem and have this Dirichlet condition be applied to only x greater than or equal to 0 and remove this condition while still holding on to this domain that I've created? Now you would expect that you'd go back to the original problem, but when you run the system, you get this. Is this a bug? No, it's not. It's actually to be expected. This is what a finite element does. What it does is internally it recognizes that you explicitly told in the domain that there is an internal boundary. I'm going to treat that as an internal boundary, and therefore that Dirichlet condition is going to get applied to that as well, right? So you need to be aware of what finite element is doing internally and how it's doing the talking, so that you can get the right results. Okay, so that's Dirichlet conditions. Now I'm going to talk about Neumann conditions. This is a little bit more complicated than Dirichlet conditions. So bear with me while I go through the math. But once I take you through the math, hopefully why we have chosen this form and why the Neumann conditions are defined the way they are will hopefully become clear. So I need to take you first through the FEM derivation. So the way technically FEM derivation is done is you have your governing equation, you multiply that with a test function. That test function in this case is the term phi here. You integrate it over the entire domain, and during the process of integration, you do this integration by parts, and you end up with a volume integral, which is the first term here, and a surface integral. Okay? And the surface integral has a form that basically comes from the governing equation. And so what internally finite element does is it treats this red part as the left-hand side of the Neumann condition, and it replaces it with the right-hand side, which is the G minus QU. So technically, it's your Neumann condition that you're looking at is this red term equal to this blue term. But what you're giving to NDSolve and to FEM is the right-hand side. This left-hand side is assumed that you already have it in the right form. Okay, so that's kind of the gotcha here. So which means that this G and Q term that you have to put in have to properly account for how this left-hand side, which is implicitly embedded inside of FEM, so you have to account so that the coefficients and everything match up properly. Okay, so time to confuse everybody. All right, let's take this simple 1D example. I'm going to apply, it's a boundary value problem, but we'll solve it using finite elements. On the left boundary, I'm going to give it a Dirichlet condition. Right side, I'm going to give it a Neumann condition. So if I give it to DSolve, it gives me back an exact solution. So it's good, we can compare it with our numerical system. The domain is just a line going from 1 to 2. And now, I'm going to give the boundary the governing equation simply just in its original form. But when I give it in this form, internally, finite element sees this, the first thing here, in the red. And therefore, that red term now becomes part of the Neumann condition. Okay? So this red term gets copied down here, and you have your G minus QU here. Okay? So which means that this is what finite element method is seeing. And so in order for you to get or satisfy this Neumann boundary condition of your original problem, you need to match the coefficients. So just a little back of the envelope calculation will tell you that G has to be 15 by 4 and Q has to be 3 by 4. Okay? So that's where the subtlety of Neumann value lies. Okay? And so then when you plug those numbers in, you get back a solution. I mean, it's within the tolerance of what FEM is producing. It's not the most accurate, but it is consistent. Okay? So if you are still with me, I want to take you through one more example that'll show you the flexibility of of Neumann value and the FEM framework and how you can specify the problems. So I'm going to take the same example, but I'm going to write it differently. what I'm going to do it is I'm going to write this system in what is called as a conservative form, meaning that I'll take this u double prime, and I'll take the first derivative out. So it'll be dx in the bracket, it'll be 3u prime of x plus 15u. Okay? So this first two terms in this governing equation will get grouped together in what is called as the conservative form, and that's what you're going to give to ND solve by applying this inactive term to it. Okay? So there's your divergence of your gradient. Okay? And when you give it in this form to ND solve, what it sees is this term here in the divergence term. Okay? Which is different from the previous example. Now you have this 15u coming in, which means now again you have to do your calculations, back of the envelope calculations, to figure out what q and u is, because you gave your differential equation in this form. So in this case, you end up with your g still having the same value, but q ends up having an additional quantity of 15 attached to it. Okay? And so you get the exact same solution. Okay? So there is significant flexibility inside of the FEM framework that you can manipulate these equations in any shape or form, but when you're dealing with Neumann conditions, it's kind of important to know what form you gave it so that you can apply the right boundary conditions. Okay, so this is one of those, another example wherein the mesh in this case comes from maybe some external source, and you don't have much control over the symbolic thing associated with it, but what this boundary mesh does have are what are called as these element markers. And so you can apply, use that information of element markers to specify the Neumann conditions or the Dirichlet conditions at those marker locations. So in this case, I don't know whether you can see it, there is red embedded in between here. Okay, so that's one set of area wherein you want to apply boundary conditions, and the black is another place you want to apply. So you solve the Neumann problem here. It takes a few seconds. It's a rather large problem, but there you go. That's the solution you have. Okay, and the reason you want to do that rather than specifying the boundary conditions is because you just don't have that information, but you do have element marker information, and that's quite useful, and a lot of people use it that way. Now, the thing I want to bring focus to is that we are doing this thing that really doesn't conform with the syntax of the Dirichlet condition. In the Dirichlet condition, we gave it the differential equation, and then we gave it the Dirichlet condition, which are the boundary conditions, and so on. But with the Neumann condition, we're actually putting it as an equality sign and attaching it to the differential equation itself. So maybe if I were to go back, you see what we're doing here. This is the differential equation, and then we're equal to this Neumann value. So why is it that we have chosen to do it in this fashion? And the answer to that is that take a case wherein maybe this wasn't, well, this will work. You have a case wherein this g takes on a value, but q is 0. And when you have that q equal to 0, then you don't have a dependent variable existing inside of Neumann value. So if you have a system of PDEs, which one of these PDEs contain that Neumann condition? You need to apply it to the appropriate PDE. And that's the reason that the Neumann condition is directly embedded inside the differential equation. Okay, so that's again one of the syntax that FEM users in Mathematica need to be aware of. All right, so enough of Neumann value and the boundary conditions. I want to talk quickly about error analysis. I'm going to show you a couple of examples, and you'll see immediately that the results seem completely weird. It's the same thing. It's a disk. The second one is an implicit region which defines a disk. I tell it to use and integrate. If you do integration on that, you get pi. So we have something to compare it to. But depending upon how we specify the region, we're getting radically different results. We're getting really good results if we give it a symbolic case, terrible results if you're giving discretized region, and well, almost terrible results if you use two-element mesh. So why is that? Well, in the first case, the symbolic region allows you to have complete control of the region that you're discretizing and allowing how the elements to be placed. With discretized region, what's happening is that the boundaries are they're curved boundaries, but after discretization, they're just linear elements, they're just lines. And so you lose a lot of accuracy when you discretize the boundaries in that fashion, because that curve is not accounted for. Two-element mesh, on the other hand, does account for that curve, but the resolution or the number of points it uses may be a little less, which is why you see a little less accuracy. So you need to be aware of how you present your region to whatever numerical system that you're solving. So what happens is, this is the disk, but when you discretize it, you're just discretizing the line. So you end up with a polygon. And all that error is this area that you're losing, right? But if you use two-element mesh, you're using second-order elements. So you're using curves, and that improves the accuracy significantly, okay? Well, what does that mean for us when we're solving PDEs? Well, one of the things any numerical analyst should do is to do things like error checking, grid convergence, all that. Finite element methods, if you're using linear elements, you should get second-order accuracy, right? I'm not going to run through this, I'll just show you. When I present case 1, which is I'm just solving a Poisson equation, but I'm giving it a discretized region. So the boundaries are only lines. So because it's only first order accurate, you get the solution when you compare it to the exact solution turns out to be h squared. But when you give it a symbolic region, everything is very well resolved, and you get a fourth order accuracy. Okay, and that's where that's what you need to pay attention to. Try as best as possible to give it symbolic region, or if not, at least make sure that the boundaries are properly resolved. Now, you need to be aware that sometimes a discretized region can represent the boundary exactly. For example, if you have a rectangle, then linear elements represent, those lines represent your boundary exactly. In that case, even if you were to give it a symbolic region or a discretized region, you'll always get a fourth order accurate result as you decrease the result. So subtleties that you need to take into account. One final thing is in error analysis is residual checking. You take a problem, solve it with finite element methods, and then you ask yourself, well, how well is it representing, if I put the solution back into my differential equation, how well is the solution behaving? Well, that's the solution, you plug that solution back into the differential equation, and the result looks absolutely horrendous. Does that mean that the solution is wrong? Absolutely not. If you look on the right graph, that's the solution with the exact solution, and that's pretty decent. But on the left-hand side, you have a residual. And the residual is not coming out correctly because when you're doing finite element analysis, the highest order derivative goes down by 1. So that highest order derivative information does not ends up having a really bad approximation in the interpolating function. Okay, and so this kind of residual checking, if you do that, make sure to keep these things in mind. Okay, and I think that's pretty much what I wanted to cover. I think we have time for for a few questions. I hope you found this information useful. And finally, from a message from Oliver from Asia. Here you go. Thank you. I'll take any questions you have. Yes, sir.
What about arbitrary domains for the solution?
Arbitrary domains for?
Yeah, you're presenting only regular domains, these spheres.
Yeah.
What about any domain?
Sure, go for it. Yeah, it'll work on any domain.
How can you define the domain?
You can define, well, if it's complicated enough, most of the time you'd end up defining it using implicit region, with various combination of predicates. You can also import your own file which contains the mesh. It'll just work. No problems at all. Disk was just an example because I wanted to keep things simple. Sir.
Is there any way you can have
I know what you're saying. My first intuition is yes, it should. But I can easily see problems arising, especially if the coefficient term all of a sudden drops out. Maybe you can set up the system so that the term suddenly drops out. I wonder what happens then. I haven't tested that, but yeah, it should be theoretically the framework should handle that. Yeah. Other questions? Jose?
A similar question. So imagine that you have a vector. You are evolving a vector matrix, and you have an inner boundary. Typically, you have to worry about continuity conditions or transversal part, etc.
Yeah.
Is your functionality able to do that automatically?
To account for the continuity condition between the interfaces?
Is it completely internally continuity conditions, or the system has a way to handle that?
If the interface is known a priori, it'll pick it up. Yes. And the way I understand it is that it'll set up the elements in the proper way so that the integration is done in that consistent order, so that you don't get these wild oscillations right at the interface. Yeah. Okay. One more, please.
In the Neumann value problems,
Yeah.
You were actually solving for the G and the Q.
G and the yeah.
So you actually have to do that manually.
If you, yes, therein lies the subtlety associated. Generally, the Neumann values in typical PDEs aren't with that condition that I put in there for the ODEs is a Robin condition. It's got the derivative and the value associated with it, and that's a synthetic problem I put together to emphasize it. But in most cases, it's just the normal derivative is equal to 0, in which case you really don't have to worry. Just set that equal to 0, you're good to go. Yeah, but if you are dealing with these complicated Robin kind of conditions, yes, please do a little bit of calculation. Yeah. Yes.
Are you using the whole reduced integration concept inside of Gauss points and very traditional finite element formulation? And then say for elliptical problems, typically solid mechanics.
Mm-hmm.
We're interested in stress being a big driver in failure mechanisms, things like that. They're actually the derivatives of the response are actually more accurate at the Gauss points than they are at the nodes.
Okay.
And so that concept is very, very common throughout that whole world.
Structural mechanics and crack. Yeah. Okay.
So can we get at that data?
The derivative data,
The
or
derivative evaluated
at the Gauss points.
The most accurate spot in the domain.
Geez, yeah, I wouldn't. Yeah.
It's definitely doable.
Yeah. So what they typically do is they form a little sub-element inside with those 4 Gauss points, and then you interpolate those values to the nodes.
Yeah.
For graphics and things like that.
Yeah.
Lots of tricks of the trade.
Right. Yeah.
For 30 years. So.
Yeah, absolutely. Well, any other questions? Cool. Let's get lunch. Thank you.